Okay, in this video I want to talk briefly about polarization. And those of you who have polarized sunglasses may be able to appreciate this also, and you may have all used polarized sunglasses. The idea behind this, though, is that any light wave that you see consists of changing electric and magnetic fields, as we've talked about earlier. And they change in a sinusoidal fashion, and they also change spherically, where you have, in multiple dimensions, where you have, let's say, the electric fields, which I'll draw in red, varying in one direction, and the magnetic fields varying in the other. So you may have something that looks like this. So you have basically all variations of how the directions of the electric and magnetic fields and how they vary. So you'll have some that are doing this as well. And you can get all sorts of, you can get multiple different waves all superimposed on each other, each with varying electric and magnetic field directions all over the board. So what happens in polarization is you have some sort of a device that acts kind of like a filter. So you can almost think of it as something, I'm going to draw it as slits, though it's not exactly slits, but it's something that will only allow light with a certain orientation of its electric field to pass through, or light that has a component of that orientation of its electric field to pass through. So this setup here will allow light, for instance, that has an electric field, well, I'll draw it in red still. We usually refer to the light's electric field rather than its magnetic field as the basis for orienting in terms of polarization. So if the electric field is doing this, then it will certainly pass through this polarizing lens. If the light has an electric field doing this, then that will not pass through. And if the light has an electric field that is doing this, then the component of the electric field that is vertical will pass through. So it will pass through that element of light, but just slightly diminished, or diminished by an amount of basically the cosine of this angle here. Alright, so that's the idea behind polarization. So what if you had, what's neat about polarization is some of the things you can do with it. What if you had one lens that, or one polarizing, it's not a lens exactly, but filter, that is oriented this way, and then you had another one, let's say that's oriented in the same way. Well, the light's going to pass through one, let's say this one's first, and then it's going to filter some out, and that same filtered light will all pass through the second one. So you'll get an intensity of about half of what you might have had if there was just plain, if you didn't have any polarizing lens. So this right here will knock out about, just one alone will knock out about half. If you put another one on, the same orientation of it, it won't knock out anything that hasn't already been knocked out. So that would also give you about half the intensity. So if you think of the intensity of the light without any polarizer, to be, I'll call it intensity 0, and the units of that would be watts per meter squared. With a polarizer in place, with one polarizer, no matter what the orientation is, if we assume a random distribution of light polarizations, I would say that the intensity after it exits the one polarizer would be about half of the original light intensity. Then what if you put two polarizers together? Well, as I mentioned, if they're aligned, then the intensity coming out of the second polarizer will be the same as that coming out of the first. But what if you rotated the second polarizer like this? So what if the first one was oriented like this? And then you rotated the second one so that it was oriented like this. What you're going to find in that case is that you'll completely block all the light. None will be able to pass. However, if it's aligned at some intermediate angle, say of this, and this, then you will get a proportion of the light that is able to pass from this one through this one. Here you get none. In the first case here, none passes both. Here you get some. Okay? And the relationship, you can imagine it has some sort of a sinusoidal relationship, because each time you cycle at a half cycle, it lets more through. And if we went through some analysis and proof, it would look like this. But it's fairly straightforward. The intensity of the light passing through is equal to the intensity of the light that would pass through 1 times the cosine squared of the angle between the two polarizers. So, in other words, in this case here, that angle is 0. In this case here, that angle is 90, etc. So given that, you'll be able to do what you're asked to do in the lab, which is to rotate the angle of the two polarizers, and then look at the intensity of the light coming through using a light intensity sensor, which comes as part of the vernier package. So that's the activity involving polarization. And I think you'll be impressed as you see the polarizers get lighter and darker as you rotate them relative to one another. It's a pretty neat phenomenon that has all sorts of applications, as you can imagine, for changing the brightness of a room or the brightness of an area. Okay,